Hello, this is Richard Collins, your instructor in ATM 101, Weather and Climate of Alaska at the University of Alaska, Fairbanks. Welcome to Unit 4, Heating the Earth. Today I want to highlight the fundamental ideas we'll be exploring in Unit 4. These three maps show the average temperatures in Alaska for the whole year, for the month of January and the month of July, and they highlight many of the processes we are considering in this unit. In the annual average temperatures, we see that the state of Alaska gets generally colder as we head northwards across the state. Maritime influence is visible in the south and along the west coast, where the climate is generally warmer than in the interior. However, maritime influence isn't that obvious up on the Arctic Ocean in the annual average and in the January average, because the ocean remains frozen and we don't have liquid water contributing to a warming of the land. In July, you see that the interior is the warmest part of the state, and this is because we have a continental climate with low elevation around the river valleys of the interior. In the annual mean and July, we see that the Alaska Range and the Brooks Range at high elevation are amongst the coldest parts of the state. However, in January, we see that there's very cold air associated with the low-lying valleys in the interior and the Copper Valley. In this unit, we're answering the question, what are the causes and consequences of heat transfer within the Earth-atmosphere system? We will be looking at the concepts of heat and temperature, how heat is transferred in the atmosphere, energy balances in the overall energy balance of the atmosphere, and energy balances and how they vary with latitude, and how local temperatures vary over the cycle of the day and the year. Temperature is the measure of the average kinetic energy of the atoms and molecules of a substance. Heat is energy being transferred. We can measure temperature on several scales. The Kelvin scale is an absolute scale where 0 Kelvin, corresponding to minus 273 Celsius or minus 460 degrees Fahrenheit, corresponds to the temperature when the atoms and molecules are at rest and have no kinetic energy. This is the lowest temperature that we can achieve, and it's called absolute zero. Increasingly, meteorologists do not use the liquid thermometers that we see in textbooks. They use electrical thermometers where the electrical properties vary with temperature, just as we're using them in this class. Thermometers only measure the ambient air temperature accurately if they are properly set up in the shade and well ventilated. If not, you're just cooking the thermometer in a box and it doesn't represent the air temperature around it. And finally, on the lower right corner of the slide, we have the conversion equations for Fahrenheit, Celsius, and Kelvin. Heat is transferred by conduction, convection, and radiation. Conduction, where we have direct contact between the hot and cold material. Convection, where we have a fluid between the hot and cold material, and the fluid rises in a convection pattern as it's warmed and then falls cooler and transfers the heat in a convection bubble. And finally, by radiation, where the hot object emits more radiation toward the colder object, which absorbs that radiation. All three processes are at work in the atmosphere. And it's important to remember that heat transfer is always from the hotter, higher energy object to the colder, lower energy object. We find again that water has unique properties in the atmosphere, in that it exists as a solid, liquid, and gas at atmospheric temperatures. When water changes phase, there is an energy change as the water molecules become more tightly bonded as they go from liquid to solid, or they become more loosely bonded as they go from liquid to vapor. To melt ice, we have to supply energy to break bonds without raising the temperature, and this is an example of hidden or latent heat. When water condenses from vapor to liquid, heat is released, and this is an important part of the energetics of cloud formation in the atmosphere. Continuing the idea that water is special in the atmosphere, we also find that water requires more energy than other materials to warm and releases more energy than other materials when it cools. Thus, we think of water as having thermal inertia. Maritime regions warm more slowly than continental regions in summer and cool more slowly in winter. Thus, the seasonal range of temperatures is much lower in a maritime city like San Francisco than a continental city like St. Louis, even though they have the same average temperature over the year. We see similar behavior between locations in western Alaska and interior Alaska. We can follow the pathways of solar radiation and terrestrial radiation in the Earth atmosphere system. Averaged over the whole globe, 49% of the incident sunlight is absorbed at the surface. The atmosphere-Earth combination has an albedo of 31%, where 31 units are reflected by the air, clouds, and the surface. The surface itself has an albedo of 14%, where 57 units of solar radiation are incident on the ground and 8 units are reflected to space. In the terrestrial radiation, the strength of the greenhouse effect is seen in the following way. Notice that there are 95 units of radiation emitted by the atmosphere toward the ground, incident on the ground, and this compares with 49 units of direct radiation from the sun. We also highlight the role of two non-radiative processes, a sensible heat flux associated with conduction and convection, and a latent heat flux associated with evaporation and condensation of water vapor. These combined fluxes contribute about 30 units of flux. You can use slide 7 to begin playing climate scientist as you think about how fluxes of radiation would change as different elements of the climate system change. What happens if the surface albedo changes? If the Earth was covered with white snow uniformly, that albedo would go to 100%. What happens when greenhouse gas concentrations increase? Then the fluxes associated with the greenhouse gases should increase and change temperatures in the system. You may also think about how your local region differs from the average. How does this picture compare with Barrow in November? The table shows that in the slide 7 we have a balanced model of radiation and energy, and the Earth's average temperature would remain constant from year to year. Current climate change studies indicate that the balance is not perfect and that the atmosphere-Earth system is gaining 0.3 units of energy a year as greenhouse gas concentrations increase. In a system where we're looking at 100 units, finding that 0.3 units as an average over the globe from real experiments is one of the greatest experimental challenges. We've just looked at the balance of energy averaged over the entire Earth for the entire year. Now we look at the balance of energy as a function of latitude averaged over the year. We see that the tropical regions receive more energy from solar radiation than they lose by emitting terrestrial radiation. The polar regions lose more energy by emission through terrestrial radiation than they receive through solar radiation. Thus, the tropical regions have a surplus over the year, the polar regions have a deficit over the year. If this was left to its own devices, the tropical regions would become hotter from year to year, and the polar regions would become colder from year to year, and we would get a huge contrast between the tropics and the poles. In reality, energy is transferred from the warmer region to the colder region, and this transfer of energy is what sets up the major weather and storm systems in the atmosphere, as well as the major energy balance. Also explains the daily and seasonal variations of temperature. Each day, the highest temperature is found not at noon, but at mid-afternoon, while the lowest temperatures occur not at midnight, but near sunrise. The reason for this is due to the balance between the solar energy being absorbed and the terrestrial radiation being emitted. As the sun rises through the morning, there is more solar radiation incident on the ground. While the ground warms, we end up with a net surplus of radiation and the ground continues to warm. As the ground warms through late afternoon, the thermal emission now begins to exceed the solar radiation absorbed as the sun falls in the sky in the late afternoon, and eventually we go from a surplus to a deficit and the ground begins to cool at about 4 o'clock in the afternoon. After sunset, the emission continues and the air cools through the night, giving us our coldest temperatures just before or after sunrise, when we begin to get solar radiation again beginning to create a surplus of energy. Seasonal variations work in the same way, with a lag where warmest temperatures are found in July and coldest temperatures in January, even though the sun is highest in the sky in June and lowest in the sky in December. The seasonal variations are, as expected, greatest at high latitudes. It's important to remember that it's not all about radiation. Occasionally, transport of cold and warm air can define the temperature and beat the effects of radiation locally. The advection of cold or warm air can beat local radiative heating and cooling. In interior Alaska, warm air is advected into the interior and causes winter temperatures to jump 30 degrees Fahrenheit during Chinook episodes. In the lower 48, cold air transported from Canada down into the southern United States can cause severe damage to orange crops in the middle of winter. Finally, some closing thoughts in our summary. Temperature represents the average kinetic energy of atoms and molecules in a substance, and energy transfer can occur by conduction, convection, radiation, and latent heat. Again, we've seen that water is different, both in terms of its phase changes, which bring latent heat into the picture of energy, but also its specific heat, in terms of how it moderates climate in maritime regions. The greenhouse effect is evident in the energy budget, as the infrared heat flux is larger than the direct solar radiation flux in the energy budget of the Earth. However, the energy balance in the Earth is not balanced at every point on the Earth, and it's not balanced at every time. If it was balanced at every time, we wouldn't have days get progressively colder in the fall and progressively warmer in the spring. These energy imbalances drive our weather, and the most dominant one is the energy imbalance between the tropics and the poles drives the major pattern of storm systems on the planet. Finally, energy imbalance drive temperature changes as well in both our daily and seasonal cycles.